So hello everyone, welcome back to another particular lecture series of our IR spectroscopy course, and this is the class 4. So in our previous discussion we are talking about the IR spectroscopy, different kind of modes of vibration and all. So in this particular class we are talking about the different fundamental vibrational modes, and we are discuss about some important IR peaks that you have to remember, because that particular IR peaks are actually very useful when you are solving IR related questions. So first we are talking about the fundamental vibrational modes. So first of all, that number of vibrational modes can be determined by the number of vibrational modes. So the number of vibrational mode is nothing but 3n minus rotational mode plus translational mode. Now this 3n is called the degrees of freedom of any kind of molecule, whereas the n particularly suggests is the number of atom present in that particular molecule. For example, if it is a monoatomic molecule, then the n value is 1. If it is a diatomic molecule, the n value is 2. If it is a triatomic, then n value is 3, and so on. And rotational mode and translational mode, how calculate? So basically, if your molecule is linear, then the rotational mode is 2 and the translational mode is 3. And for the non-linear atom, the rotational mode is 3, translational mode is also 3. Now, the rotation changing between rotational mode is for the linear atom, the rotation can be observed between the x and y axis only. Z axis doesn't interact. But in the case of non-linear, there is a three different axes actually used to rotate the particular molecule, and that's why there is a three rotational mode is there in non-linear atom. So the vibrational mode can be calculated by for the linear molecule, it will be 3n minus 5, where 2 is contributed from the rotational and 3 is contributed from the translational. Now, this is something that you have to remember, and also for any kind of molecule, stretching mode is the n minus 1, where n is the already I discussed that number of molecule atom, and the bending mode is the rest of the vibrational modes are actually called about the bending modes. And for the non-linear atom, it is simple that the overall number of vibrational mode is 3n minus 6, and the stretching mode is n minus 1, and the bending mode is 2n minus 5. And for atom, it is 3n minus 3. And for activated complex, this is basically in the kinetics part, there is activated complex is there, and for there the vibrational mode is 3n minus 7. Now we are just do a small exercise to determine the number of vibrational mode and number of stretching bending mode in certain compounds. So we have done this particular exercise. So as we already know that number of vibrational mode is 3n minus 5 for the linear and 3n minus 6 is for the non-linear. Okay. So now first, and out of which that stretching mode is n minus 1 and the rest is the bending mode. So first of all, it is written as H2O. So for in the case of H2O, as we know that H2 is a non-linear structure and it is something like this. So what happened that it is a non-linear, so the formula will be this only, and then number of atoms present H2O is 3, that means the n is 3. So number of vibrational is 3 into 3 minus 6, that means 3. That means in H2O molecule there is a 3 vibrational mode is present, out of which stretching is n minus 1. N minus 1 stretching means 3 minus 1 equal to 2, and the bending is rest, like number of total vibrational mode is 3 and stretching is 2, so bending is 3 minus 2 equal to 1. Okay, similarly now we are talking about the NH3. NH3, as we know, this is also a non-linear molecule, and here the number of atoms is 4, that means the n is 4. So the total vibrational modes are 3 into 4 minus 6, and this 6 contributed from the translational motion and rotational motion. So that means it is coming, total number of mode of vibration is 6, out of which stretching is n minus 1. That means the 4 minus 1 equal to 3, and total vibrational mode is 6. So that means the bending is also 3. 6 minus 3 equal to 3. This is stretching and this is bending mode of vibration for the Na is 3. Similarly, I just simply rub it off for the H2O case, and we'll try for the next one. So next one is our SO3. SO3 is also a nonlinear molecule. So you need to know about the chemical bonding part of this particular part, that how the molecule is linear or non-linear, so that you can solve this particular question correctly. So for the case of SO3, it is similar like of NH3 also. So it is also have the V equal to 6, and the stretching mode is 3, and bending mode is also 3. As similar like NH3, because it also have 4 number of atoms. That means N is the 4 and a non-linear molecule. Okay, now the C2H2, this is interesting because as we know that acetylene is a linear molecule. That means now number of vibrational mode can be determined by using the linear formula, that is the 3n minus 5. So C2H2. So we know that here the number of atoms present in 4. That means number of atom here is 4. That means it is should be 3 into 4 minus 5. Now here that means 7 is the number of mode of vibrational mode for acetylene is 7. Now if we talk about the stretching mode is n minus 1. That means the 4 minus 1, that means it will be 3, and the rest mode of vibration are the bending mode of vibration. Bending, that means 7 minus 3 equal to 4. So now there the ethylene molecule is there. So for the case of ethylene, I just simply do it here. Okay, okay. For the ethylene molecule C2H4, so this is also a nonlinear molecule, and the number of atom present here is 6. That means the number of vibration is equal to 3 into 6 minus 6. That means 12. That means the ethylene molecule have 12 mode of vibration, and out of which the stretching is the 6 minus 1, that is the n minus 1. That means the 5, and bending is 12 minus 5 equal to 7. So this is for the ethylene molecule, and the last one is the SF6. So we just simply quickly do the SF6 molecule. Now you can try for the any kind of molecule for that particular determining the number of vibrational modes. So let us talk about the SF6 here. SF6 is, you know that there is a 7 atoms are there, so that means the N is the 7, and also SF6 is a non-linear molecule, it's the octahedral structure. So that means we can say that the number of mode of vibration is 3 into 7 minus 6. So that means it is 15 mode of vibration, out of which the stretching mode is n minus 1, that is the 7 minus 1 equal to 6, and rest all are bending. 15 minus 6 equal to 9. So that's the process that you have to determine the number of vibrational mode, number of stretching and bending modes for any kind of molecule. So I hope this all example are clear to you. Now let us move on to the different part, and this particular slide is very important for understanding or solving question in the IR. So as I already discussed about the Hooke's law, from the Hooke's law you can understand this particular equation where the wave number, that is a nu bar, it is equal to 1 by 2 pi c root over k by mu, where is the k is nothing but a force constant of the molecule, that means the bond strength, and the mu is the reduced mass of the particular molecule. So from this particular Hooke's law equation, we can say that nu bar is directly proportional to the force constant and inversely proportional to the reduced mass. And the reduced mass, how can we calculate? We calculate reduced mass by using this particular formula. Now the interesting thing is that from this particular relation, you can solve n number of question in the IR spectroscopy, because that where the more the force constant, that means the more the wave number, that is the nu bar, and also less the reduced mass, then more the wave number, that is the nu bar. And so that means how that nu bar varies with different factors. In the case of organic molecules, that nu bar is directly proportional to force constant. If any bond force constant increased, then the nu bar of that particular bond is also increased. Similarly, nu bar is directly proportional to the bond strength. Like if the bond is double bond or triple bond, then the nu bar value is much higher over other bonds. Also, nu bar is directly proportional to the S character of the particular bond. Also, nu bar is directly proportional to bond angle, and nu bar is inversely proportional to the bond length. So this particular slide section is very important to solve IR related questions, and this is very important. So now let us talk about the different IR peaks. Now this particular peak you have to just simply mug up, because if you completely do the mug up of this particular slides, then it will be very easier for you to solve IR related question. And also in the exam point of view, there is a merge question is coming, which contains the some kind of IR values as well as the NMR values. So you have to remember this all the values, so you can solve that particular question easily. So first let us talking about the alkanes value. Like alkane, there is a CH stretching is there. If the CH stretching, the value is nearly about 2850 to 2960 centimeter inverse, is the wave number. And CH bending is this. It is not that much important, but the stretching value is very important. Now alkene's case, if we check about the CC double bond stretching, it comes to the 1620 to 1680 centimeter inverse region, and the CH stretch sp2 is come to the 3000 to 3100 centimeter inverse. And bending is not that much important, but I would suggest that remember that values also. For the alkynes CCH stretch is the 1300 centimeter inverse, and the CC triple bond stretch is uh, 2100 to 2260 centimeter inverse. Now this is very important, aromatic peaks. Aromatic ring, you have to remember that this one the very important, where the CC stretch, CC double bond stretch for the aromatic ring is nearly 1450 to 1600 centimeter inverse. This value is very important. Also, let us talk about some other functional groups stretching frequency. Like for the case of alcohol, it will be 3200 to 3600 centimeter inverse, and this particular are the broad. Like basically it is hydrogen bonded OH is broad, otherwise it will be a sharp peak. So I will discuss in the next lectures obviously. Next, we're talking about the CO stretch. In the case of alcohol, it will be 1000 to 1260 centimeter inverse. For the carboxylic acid, it is also OH stretch. This is also having the hydrogen bonded, and it is actually due to the hydrogen bond, the bond is very broad, and the peak is something around this region. Amine case is also NH stress is observed between the 1300 to 3500 centimeter inverse. Also the NH bending is observed. And in the case of aldehydes, aldehyde is very important. Like CO stretch is this 1725 to 1740 centimeter inverse, and CH stretch is not that much important. This is very important. And we are talking about the different carbonyl functional group. For ketone, it is 705 to 725. Esters are a little bit of higher. Similarly, you can check here the amides also. And cyano group, it is the this region, and anhydride, it is much higher. CO stretch is nearly 1820 centimeter inverse. So here you can see a simple chart where the acid chloride have the most new CO, then esters, then aldehyde, then ketone. Ketone is lesser because of the plus I effect of this two particular R group that we'll discuss in the factors in IR spectroscopy, which affect the IR spectroscopy. And the amide is much lower because of the uh, this partial double bond characteristics. Actually the new CO value is decreasing. So this all the important factors that actually affects the IR value we'll discuss in our next class. So before that, we are just simply do a simple exercise. Now here it is a simple ketone. So as we know that the simple ketone is near about the 1745. Okay. And also, if we talk about this particular, this is nothing but ester having the higher value over ketone, that means this, and the anhydride having the most higher value, then it will got 1865. Now you can check here from this particular value, and not only that, that every time the value actually lies between this range, sometime it is little higher and sometime it is little lesser, depend upon the compound, but more or the less, this is the rough approach to check about the IR groups. Okay, so the correct answer is this for that particular question, and this particular question come in the NET December 2017. So with this, we have to end this particular class. In the next class, we are talking about the different factors that actually affects the IR value. Mostly in the next class, we are talking about the hydrogen bonding mode, and then we are talking about the different kind of effects. So thank you for listening.